This video demonstrates how to efficiently label and train defect segmentation models using Mech-DLK to accurately detect small surface defects on workpieces. In such tasks, the defects are often extremely small and scattered across the surface. As a result, training directly on the original images often yields poor performance, since the model fails to recognize their key features. To improve the model's detection capability, the original images should be divided into smaller patches of uniform size before training. This increases the relative visibility of each defect within a patch, helping the model better learn the defect features, and significantly improving detection accuracy. In this video, laptop housings are used as an example, to demonstrate how to train a defect segmentation model, to detect and locate bright spot defects, and determine whether the housings meet quality standards. The overall process consists of 7 steps: data collection, data processing, data labeling, image size processing, model training, model validation, and model export. Now, let's go through the specific process. The first step is data collection, which is the preparatory work. During image acquisition, adjust the 2D exposure mode and white balance settings to improve image quality based on project requirements. In addition, adjust the amount of data collected based on the defect types and their degree of discrepancy. After collection, select only high-quality images for labeling and training. Please refer to our documentation for details. Next, proceed to the data processing. Open Mech-DLK. Create a new project. Select the Save path. After entering the project interface, add the Defect Segmentation module. Import the previously selected high-quality data. Analyze the image data. The target of this project is to detect small bright spot defects on the surface of laptop housings. These defects are extremely small and difficult to recognize. Additionally, a review of the overall dataset shows that the defects appear at random locations on the housing surface, making it unsuitable to define a fixed ROI. Then, create classes. The classes can be created based on the defect type or feature. For this scenario, only one type of defect needs to be recognized, with no need to distinguish front from back or other specific features. Thus, a single class is sufficient. Next, let's proceed with data labeling. Based on the project requirements, clarify the labeling rules. In this scenario, only bright spot defects need to be labeled. Given the small size of the defects, it's recommended to use the brush tool for labeling. The brush size can be adjusted according to the defect size. While labeling, try to follow the contour of the defect as closely as possible. Given the large volume of image data, it is not necessary to label the entire dataset. Instead, begin by accurately labeling a small, representative subset for training. Prioritize data with clear variations in defect location, shape, and other characteristics to maximize diversity. Now, 10 labeled images are available for initial training. Move all labeled data to the training set. An OK image can also be included in the training set to help the model distinguish between defects and normal workpieces. If an OK image is used, check it carefully to ensure there are no defects. Add the checked image to the training set. Then, split the data into training and validation sets. A typical split is 80% for training and 20% for validation. When finished, process the image size. Confirm the image size requirements. Make sure in the algorithm module, defects and their labels remain clearly visible. Initial adjustments can be made using the input image size parameter. It refers to the pixel-wise height and width of the image input to the neural network for training. The larger the image size, the higher the model accuracy. In this scenario, since the defects are extremely small, select the maximum input size. Open Zoom Preview to check the image. At the current maximum size, the defect labeling are clearly visible. However, in the original image, the defect is still difficult to see. To ensure both the defect and its labeling are clearly visible, use the grid cutting tool to divide the large image into smaller patches of equal size. This allows the small defects to occupy a larger portion of each patch, making them easier for the model to recognize. The defects in this project are very small. Thus, more patches can be generated. If a single defect is split across multiple patches, it can be adjusted using edge expansion. For detailed instructions, please refer to the documentation. Here, the grid is set to 3 by 3. Open the Zoom Preview again, and adjust the input image size as needed to ensure both the defects and their labeling remain visible. After the large image is split into multiple smaller patches, the total number of training images increases, which may slow down the model training and validation process. To address this, use the grid selection tool to automatically select only the patches that contain defects. These selected patches will be used as training data, reducing the number of images to process and shortening the training time. For OK images, all patches are selected by default. You can manually adjust whether to include all patches as required. Next, move on to model training. Configure the remaining training parameters. Ensure that the adjustments in data augmentation parameters don't affect defect features. Reanalyze the defect features after image cutting. Aside from the small size, most defects appear near the patch edges. Then, begin adjusting specific parameters. Brightness adjusts the overall lightness or darkness of the image. As the lighting during data acquisition can't cover all conditions throughout the day, the brightness range should be extended to improve model adaptability. In this scenario, lighting conditions are moderate. However, since bright spot defects are similar in color to the laptop housings, overly high or low brightness may reduce contrast and make defects harder to detect. Thus, adjust the brightness slightly to improve data stability under varying lighting conditions while preserving key defect features. Contrast controls the difference in gray levels within the image. Given the low contrast between defects and background in this scenario, slightly increasing contrast helps enhance visibility. Keep the adjustment minimal to avoid losing defect characteristics. Next, adjust the parameters related to object pose, including translation, rotation, and flip. Translation moves the entire image horizontally or vertically by a certain distance. Rotation means turning the image around a specific point by a set angle. Flip refers to flipping the image horizontally or vertically by 180 degrees. As many defects are located near image edges, enabling translation or rotation may move them out of the detection range. Thus, leave both options unchecked. Since the defect characteristics are not affected by horizontal or vertical orientation, flipping parameters can remain at their default settings. Scale adjusts the image size proportionally. Disable this parameter as increasing it may cause small defects to blend with brighter backgrounds. Lowering it too much can also make the small defects even harder to detect. Then, configure the training parameters. This project requires high accuracy, so set the model type to high accuracy. Input image size was configured earlier and doesn't need further adjustment. Epochs refers to the total number of training iterations for the model. The defects in this scenario are hard to detect, so set 500 or more for better training. Other parameter values can remain at their defaults. Since model fine-tuning is not involved in this scenario, leave it as default. Click OK to save the parameter settings. Once configuration is complete, start the training. The show chart function can be used to monitor the accuracy curve. Combine this with the accuracy values to determine whether the results meet the required precision. Training has now completed all scheduled epochs. As shown, accuracy has stabilized and loss is low, which meets the requirements. After the training is completed, evaluate the model performance by combining validation results with segmentation outputs. Use both validation statistics and inference results of the defects to check for any missed or incorrect detections. Start with the training and validation sets. Zoom in on the images to check the defect inference results and evaluate detection performance. As shown, both sets currently demonstrate good recognition performance. Then check the test set, which evaluates the model's generalization and requires close attention. After reviewing the current test set, the segmentation results are generally accurate. 2 false detections are found in image 44 and image 62, where the model incorrectly identified OK data as defects. No missed detections were observed. To correct the false detections, first label the full image as OK. Then, use the grid selection tool to select the corresponding patches and add them back to the training set for retraining. The false detections have been labeled. Add the updated data to the training set. If missed detections are found, additional labeling is required. Note that the entire image should be labeled, including both detected and missed defects. After that, add the image to the training set for retraining and validation. Labels can be added in small batches through repeated iterations until all detection results are satisfactory and the model performs well. Then, retrain the model. Before this, ensure the ratio between the training and validation sets remains within an acceptable range. When finished, validate and check the data as before. Currently, validation is complete. Check the results again. The model's defect segmentation performance in this scenario meets the requirements. Thus, export the trained model. Now, the high-efficiency training of the small defect detection model under the Defect Segmentation module is complete. You can also refer to our documentation for more details about efficiently training defect segmentation models.